Hello everyone. Now we are going to see the part of your application of shift registers. So shift registers are normally used for conversion for conversions in ADC/DAC devices like a parallel to serial conversion or serial to parallel conversion. Again, their shift registers are used along with the additional gates to generate the sequence of zeros and ones. So it is also called as a sequence generator. Also, it is used as a counter. So these are the types of counters based on the type of output of your rightmost D flip-flop is connected to serial input. So Ring and Johnson counter are two various application of your shift register. Okay, so most of the basic of your ring counter we are going to see over here. Ring counter, the main application of your shift register is, so ring counter, as the name suggests, it counts the values, binary values, and perform the ring operation. Okay, so how it going to perform? So serial in, parallel out shift register in this for this ring counter implementation, serial in, parallel out shift register is used. So it accepts the data from outside in a serial form, and it requires n clock pulses in order to shift the n bit data. Okay, if you want to perform the n operation on this number of flip flops, so you have to require the n clock pulses. So it is called as a n bit ring counter, and which is performs the similar operation, but the only difference is that the output of the rightmost D flip-flop is given as an input to the leftmost D flip-flop instead of applying data from outside. See over here in this diagram, the clock pulses are applied over here. Yes, regular shift resistors are there. CPO is we are going to use. So Q2 is generated over here, Q1 is generated over here, Q is also generated. So this is a parallel output. Okay, but this Q output is passed to the D flip-flop, that is leftmost LSB output is applied to the MSB input. Okay, MSB input. Okay, so it is perform a ring connection. Okay, ring connection. Okay, so clock for ring counter produces the pattern of zeros, zero, and it repeats for every n clock cycles. So block diagram of three ring counter is shown here. So 3-bit C4 is shift register is here. Yes, D flip-flop is connected to the serial input of the leftmost D flip-flop. So first of all, consider initial stage is Q2 having a 0, Q1 having a 0, and Q0 having a 1. So here is the input 0, 0, and 1. So Q2 and Q0 are MSB and LSB. Q0 is the LSB, and D2, this is your MSB. Okay, respectively. You can consider it as a Q2 as a MSB. So how it going to work? So first of all the flip-flops become 0, because 0 0 1 is applied to over here. Initially the value is given to you, so at the 0th clock pulse 0 0 1 is applied to 0 0 0 flip-flop. Okay, now see, on the first clock cycle this LSB output is passed to the flip-flop 1. Okay, and whatever as per the functioning of your D flip-flop, whatever the input is given, the output will be generated. So this 1 is passed to the MSB side, so it will become 1 0 0, because these two zeros are shifted over here. On next clock cycle 0 is applied to over here, so 0 1 0 is generated. The 0 is applied to over here, so 0 0 1 is generated. So this is your 3-bit serial in parallel. So after the 3 clock cycle, it will generate the original resultant value. So it will count the value up to 3 clock cycle. Okay, 3 clock cycle. After, because after 4 clock pulses, that is third clock cycle, it will generate the same value which is having a initial value. So it is performed the ring operation. So that is why it is called as a ring counter. Okay, because it counts the value. See over here 0 0 1 first time, so this is nothing but your counting. Okay, so after the 3 counting, it will generate the serial similar output which is having a initial output. Okay, so this is all about your ring counter, and the next part is a Johnson ring counter. So it is also called as a twisted ring counter. Twisted ring counter, that means The only difference is that instead of output Q0 assigned to D flip flop, here Q0 bar is complementary output is assigned to over here. Okay, so second application is your Johnson ring counter. The operation of Johnson ring counter is similar to ring counter, but only difference is that output of D flip flop is given to the instead of normal output, the complementary output is assigned to D flip flop. Okay, so it required two n clock cycles for performing the repeat operation. So it is also called as a twisted ring counter because we are not going to give the same output. We are going to complementary output to the flip flop side. Okay, so there is a situation, consider again 3-bit C4 shift register and Q2, Q1, Q0 in initially having a 000. So 000 is applied over here. Okay. Now on the first clock cycle, this LSB is 0, but we are not applying the 0 value. We are applying the Q bar. That is, these two input, outputs are complementary to each other. So if the LSB is 0, then we are going to apply the 1 on the MSB side. So one value over here applied over here, so it will become 100. For next clock cycle, 0 is again there, so 1 is applied over there because complementary, and we are going to shift each and every bit. So 110 it will become. For last 0 is there, so it will become a 111. Okay, because complementary output is there. Now see over here, this is 1, so complementary output becomes 0, so 00011 is over here. For this one, 001, because we are shifting this bit also, and for last one, 000 is given. So see, for a twisted counter, it will require the 7 clock pulses from 0 to 6. The 7 clock pulses are required to get back into the initial stage. Okay, 000 is over here, so it will get back to the initial stage after the 7th clock pulse. Okay, that is 6 clock pulse, 7 numbers, 0 to 6, that is 7 clock pulses. And so it is also called as a twisted ring counter, that is Johnson ring counter or twisted ring counter. So these are the applications of your shift register.